Okay, I'm going to talk about quantum mechanics, and we're in now what we're called the second quantum revolution. Well, what is that? It's now 100 years since modern quantum mechanics was formulated, and the laws of quantum mechanics haven't changed since this early period. And all the tests of them have shown so far that they're correct. But the key thing is, just because we know the laws of quantum mechanics doesn't mean we know immediately all the kind of strange things that can be done with quantum mechanics. It took a long time to understand fully what we could do with electromagnetism, well after Maxwell had finished his equations, and that led to a whole technology of the last century. People now think we're in the second quantum revolution, and this is where we've actually changed our main view of quantum mechanics, which originally people would have thought quantum mechanics meant the Heisenberg uncertainty principle, interference, but now it seems that the property of entanglement is the property at the heart of this second quantum revolution. And it's actually a property pointed out, a central property of quantum mechanics pointed out by Einstein, and it was a thought experiment and an attempt to suggest that quantum mechanics couldn't possibly be a correct theory on a fundamental level. But now it's viewed as the fuel of the possible future quantum information processors. So, of course, Einstein got his prize not for relativity, but for his early contributions to quantum mechanics in the photoelectric effect. But by 1935, he'd fallen out of love with quantum mechanics. And he pointed out this entanglement property, which he called spooky action at a distance, but which Schrödinger now calls it entanglement, as a much more neutral term. This was a property that if I have two quantum systems, which are like a spin up and a spin down, that are well separated, but started off in a joint quantum state, if I do a measurement on this one, it implies what would be the result of a measurement on the other half of the system a long way away. And Einstein thought that was some kind of violation of relativity, but in fact it isn't, because there's no actual information flowing between the distant systems. So Einstein thought that if his thought experiment was carried out, it would eventually show that quantum mechanics was not a true description of nature. But we now know, of course, that the experiments were eventually done, and they led to a Nobel Prize in 2022 for rather old work, starting off with John Clauser, who took John Bell's analysis of Einstein theory, of his experiment, and did the first work on it, and a more fuller experiment later by Alan Aspey. And so quantum mechanics was correct, and it showed entanglement does exist over large separations. They managed to achieve that with photons, light, which can travel long distances without interacting with the environment. But the problem with entanglement over long distances as opposed to atomic distances is it's very fragile against decoherence. So if we want to work with it, we have this problem of fragility. So quantum mechanics has continued to deliver surprises. And one of the surprises, at least for me, that I was involved with was what's now called topological matter. So what is topological matter? We can say that it differs from ordinary matter because it's got some property, which in some sense is related to entanglement properties, which can be described by a whole number, an integer. Maybe ordinary matter is described by a boring number like 0 or 1, which maybe are not really that boring mathematically, but if the state of matter is described by a different whole number, there has to be a boundary between the regions where it has a non-trivial number and the trivial number. You can't go continuously from 0 to -2, as in this picture. So the topological matter often has this very interesting kind of edge states at the boundary between the regular matter and the topological matter. And it also has a kind of robustness because you have to do a certain amount of damage to something to change it from -2 to 0. And a classic example in mathematics is this classification of closed surfaces by the number of holes in it. So the number of holes in a surface, like a donut, is clearly, at least on a scale much larger than atomic scale, where you can think of the donut as a smooth object. The number of holes in it is a topological number. You can have 1 hole, 2 holes, but you can't have 0.6 of a hole, okay? And these kind of topological properties, they're kind of robust against change. To change a football into a bagel, I have to punch a hole through the middle of it, which requires a certain amount of work and destruction to be done. So this is a kind of robust property, and it's at least been hoped that we can use topological materials to use their robustness to protect us against loss of their quantum state or loss of the quantum information to the environment. So most of these kind of new discoveries in quantum mechanics are kind of unexpected and accidental. No one really had thought about this topological matter idea until it emerged. And my own work, for a whole lot of interesting accidental reasons, took me in the neighborhood of this problem. And it was a problem very kind of abstract to do with a quantum magnetic system. But before, people thinking about magnetism really hadn't built entanglement into their pictures of magnetism. And it turned out that in the system I looked at, entanglement played an interesting role, that instead of the atoms, the magnetic atoms just being lined up with their magnetic spins pointing up and down, the magnetic spins kind of separated. A spin 1 atom had 2 spins coupled in the parallel state. They kind of separate to form a bond, and half of the spin is left at one side of the atom of the chain, and the other half at the other side of the chain. That turns out to be typical of this edge. The edge between the entangled region and the unentangled region has this spin 1/2, which is half of the original spin left there. Okay, this was actually pretty controversial at the time for kind of internal reasons in the magnetic community, but it led to a lot of controversy, but controversy is always very good in science, and lots of new methods, both theoretical and experimental, were used to weigh in on this controversy. And finally, one of the key things in modern materials is that now the material scientists have got so good they can actually build the toy material, the toy models that theorists use to play with and find interesting things in. So this was and the basic picture, topological picture, is rather straightforward. If I think of a line of people with their joining hands, hands usually come in pairs, but then there's a free hand left over at each end of the chain. So where's that got to do with the more modern developments? Well, there's an amazing thing called Majorana zero modes, which go back to ideas of Majorana, who was one of the, I guess after the early quantum mechanics, he came up with this so-called Majorana fermions, which are essentially splitting a fermion into a real and imaginary part. And basically, it has a remarkable feature that you can think of an orbital, a box, which is either empty or filled as a qubit. It has 2 states, empty or filled. And the amazing thing is you can pull this thing into 2 half boxes. When you split the box up, the orbital, you can't see anymore whether it was initially empty or filled, so the information in this qubit has been hidden from the environment. And this is actually at the heart of at least one attempt to build a quantum computer, the Microsoft one, which is attempting to use this to have topological protection, which would, if it can be made to work, would on paper at least solve some of the problems of decoherence. So anyway, this is Microsoft have announced an architecture for this, but it's not quite clear how much it actually is working. So the jury is out on this thing, but it's an attempt to do this thing. And so how does this work? It actually relates to the original spin chain I showed you, that we couple a one-dimensional system, in this case a chain of atoms, to a superconductor. And this Majorana idea that you can split an electron orbital into two parts, a real and imaginary part, which are here purple and green, has the feature that when you apply a superconductor to it, you can re-zip together the real and imaginary parts, but using from neighbors, and get left with half a Majorana zero mode or half an orbital at either end of the chain. And so this is a kind of rather amazing idea in quantum mechanics. It's been shown, at least virtually, in simulations with qubit arrays. And we're still waiting to see whether it will actually lead to any kind of quantum computing devices. So finally, that's just one of the attempts to build a quantum computer, but there are, of course, many other which are progressing much further, much faster. Nitrogen vacancies in diamond, ion traps, transmons, etc. But finally, quantum computing is not the only new development coming out of this new study of qubits. Well, actually, the qubits coupling to the environment can be enhanced to do incredibly accurate measurements. And we heard that either by letting atoms drop, you can measure the gravitational field very precisely, maybe detect mineral deposits. And the other thing is just measuring magnetic fields with these qubit devices like nitrogen vacancies in diamond have been proposed to give you a fingerprint to the Earth's magnetic field at each point on the surface of the Earth that you could then substitute for GPS to use AI to give you a fingerprint and tell you where you are in case the GPS is shut down for some reason. So finally, there's a lot of new developments in quantum, and thank you.